Morning, everyone.
Morning.
Good morning.
Today we're actually going to be talking about electron configuration. So let me pull up the whiteboard so we can go over it. So what do you guys remember about electron configuration from 1A?
The S, P, D, and F blocks.
Right, yeah, good job. The S, P, D, and F blocks, right? So we have S, right, P, D, and F. Now, when it comes to our shapes, do you remember how our S looks like when it comes to our atom?
No.
So remember our S is our sphere. Our P looks like a dumbbell or like an infinity. Our D, so what does our D look like? If that rings a bell.
Is it like the four? Can I explain it? Like
Yeah.
like two eights that kind of overlap.
Right, it's a 4-leaf clover, right? So it looks like this. I'm so bad at drawing. And then our F atom or our F um, section is super duper complicated. So we can't even draw it because of that. So remember, our electron configuration is for us to help us see how electrons are arranged in atomic orbitals for a specific element. Remember that. So like we said, there are 4 types of subshells. And our subshells we said are S, P, D, and F. Now, when it comes to the amount of electrons that each subshell can hold, let's start with S. So how many electrons can our S subshell hold in one orbital?
Two.
Right, 2. So we have 1, 2. What about our P?
6.
Right, 6. We have 3 orbitals, 1, 2, 3, and it can hold up to 6 electrons. What about our D?
10. N.
Right, it has 5 orbitals, 1, 2, 3, 4, 5, and it can hold up to 10 electrons. And our F?
I don't remember if it was 12 or 14.
All right. So 14 electrons. So it has 7 orbitals. 1, 2, 3, 4, 5, 7. And it can hold up to 14 electrons. So the thing with chemistry, everything comes together. So the reason that we go over electron configuration is because we also go over quantum numbers. So I believe Dr. Henry went over one quantum number, and a quantum number. So let me give you an example. Mm, see. Can I change the page for this one?
Yes.
Okay. So there are 4 quantum numbers, and then we'll go back to electron configuration, and then we'll see how everything relates to one another. So let me tell this quantum numbers. Ooh. So there are 4 quantum numbers. And I believe n, you guys have been over n. And the n quantum number is also known as the principal. Oh, I can't spell principal. quantum number. And this quantum number is actually, it's associated with energy. It's associated with the energy level within an atom. So that's our first quantum number. Oh, I'm so bad at spelling. And now our second quantum number is our, it's kind of like a little cursive L. It looks like this. And that one is called our angular momentum quantum number. So let me write that down. Angular momentum quantum. And with that one, our angular momentum quantum number, that one is usually, it's, well, not usually, but it is associated with our sublevel. So let me write that down. Associated with a sublevel. And we'll do some examples so you guys can see how each one works within our electron configurations. And then we have the third one. The third one is an M, and there's like a little L here as a subscript right here. And that one, we call it the magnetic quantum number. And that one is associated with the specific orbital within the sublevel. Associated with the specific orbital within the sublevel. And then our fourth one, our fourth quantum number is going to be, again, another M, but instead of an L, there's a little S as a subscript right here. And this just tells us our electron spin. And again, I said, well, we'll go over some examples. Electron spin. So those are the four quantum numbers that we work with, that we're going to see throughout chemistry or throughout this section. There's also one important thing that we also have to keep in mind. It's called Hund's rule. I'm not sure if you guys remember. Does that ring a bell? Hund's rule. Do you guys remember anything about it?
No.
Okay, so for Hund's rule is that it usually states that whenever you're adding electrons to any orbital within the same energy, and you guys have done this, you need to make sure that that they are parallel spins. So meaning that whenever, let's say you have a homework right there that they're telling you, oh, at the electrons, or due to this electron configuration, how will the electrons be rearranged? So you always have to make sure that your electrons are, opposite to one another. So with electrons, we know that electrons are negative. We know electrons don't like being with each other. They're those negative people, or they're those people that just like their own space and they don't like to share. But if they have to share, they will share a space. So the way that you guys are going to fill out these spins is by making sure that each little room or each little section gets filled up first by one electron, and then you'll fill out the rest according to how many electrons that element has, or according to how the electron configuration is set. So in this case, right, so Hund's rule states that you have to make sure that you fill out each little orbital or each house first with one electron before you fill it out with another. So you never want to fill out an orbital like this. You never want to put two electrons first. So let's say that your electron configuration is, let's see, 3s2, right? So we know that there are two electrons. So let's say, so you're never going to put those two electrons in that first orbital. You're going to make sure that you spread them out first. So basically, that's all that Hund's rule states. That you have to make sure that each electron or each orbital gets filled out first before you fill it out with more electrons. So any questions on Hund's rules?
So you have to fill the orbital first.
What was that?
You said you have to fill the orbital first?
Right. So you have to make sure that, so here, let's take this as an example. So let's say on a test you get, is this the correct way to fill these orbitals? So let's say you get this electron configuration, 3s2. And there's, let's say this is A and this is B. And they're like, which one is the correct way? And A is filled out like this, and B is filled out like this. So according to Hund's rule, which orbital or which way is correct to make sure the electrons are arranged the way they're supposed to?
Would it be A?
Right. So according to Hund's rule. So what did we say about Hund's rule?
Have to fill the orbital first.
Remember, electrons don't, so think about electrons being introverts. They don't like being with people unless they have to.
Okay.
So according to that, which one would be the correct one? B, and why again? Why would B be the answer?
Because these electrons want to be by themselves.
Right. They want to be by themselves. But if they have to, so let's say you get something like 1, 2, 3, 4, 5, 3s10. So the way that you're gonna have to fill this out is, even though you know that you're gonna fill out all the orbitals, you still need to make sure that you arrange them opposite to one another. 3s10 is a bad example. Let me try 3d9. 3d9. Oh. So if we were to fill this out, we would do again. We know that electrons are negative. They don't like hanging out with people unless they really have to. So we would do 1, 2, 3, 4, 5, 6, 7, 8, 9. And I mean, even if we were to do it, that was another bad example, but even if we were to do it like this, I know it would be correct. Let me try another electron configuration. Let's try 3d8. So here, let's, A would be Hund's rule and B will not be Hund's rule. So if we were to follow Hund's rule for A, this is how it would look. So 1, 2, 3, 4, 5, 6, 7, 8. And so this is Hund's rule for A, right? And let's do it without Hund's rule on B. If we were to fill it by orbital instead of spreading out the electrons. So 1, 2, 3, 4, 5, 6, 7, 8. So see how there's a difference here? These are arranged differently compared to B. And A was following Hund's rule. So on a test, if you get a question like this, they might trick you by filling it out like B. They would be like, oh, maybe B is correct because there's still 8 electrons. However, you also have to keep in mind Hund's rule that you need to make sure that each orbital gets filled out first with 1 electron. So keep an eye out for that if you get that as a question.
So up arrows first and then down arrows.
Right,
Basically.
up arrow, right. Yeah, because remember, this has to do with electromagnetic fields. So those spins want to be opposite with one another. So that's why we draw them that way. But yeah, you're correct.
You said it's always going to start out with an upward arrow.
Yeah. So you would start off with your upward, and then if you have more electrons, then you fill them with your downward arrows.
Okay. So for A, do we still have 8 electrons?
Right, you still have 8 electrons here. Let me, I'm not an artiste, so it might be confusing. Let's see, there we go. So yes. So,
Okay.
so you're right. So do you see the difference, Matt, between the first one and the second one?
Uh-huh.
There's still,
So,
go ahead.
well, I was just going to say the first one, you're following the Hund's rule because the last 2 electrons are by themselves.
Right?
And then on the test, they may ask which one follows the Hund's rule and which one doesn't.
Mm-hmm.
Okay.
Yeah.
And A follows it, but B does not.
Right, that's correct.
Cool.
Yeah. That's correct. All right. All right, so now we're actually gonna go into examples, and I'll break the example as we go. So you're probably like, well, okay, so like, what does all this have to do? Like, how does this correlate with one another? So again, I was talking about electron configurations, and honestly, remember, we know that electron configurations is how electrons are being rearranged and how they look in orbitals. Now with our quantum numbers, that tells us a lot. So let me give you guys an example. So let's say we have 3p5, just like that. Nothing else, just 3p5. Now the way that our quantum numbers are going to look with our electron configuration. So our 3 is going to be our n quantum number. Our p right here, that p is going to tell us the value of our L. So value of L, remember there's 4 quantum numbers, our n and our L. And that 5 is just, well, what does that 5 tell us? You guys should know this. What do we know about those exponents at the top?
How many electrons, I think? Or...
Yeah, that's correct. Yeah. How many electrons? And usually when we're drawing this out, or when we're writing out our quantum numbers, this is the electron, that 5th electron is the one that we're gonna be focusing on, and then we'll see on later on in this example. So let me write that as a side note. So we are focused on this electron. And you'll see why. So again, let's write our quantum numbers. So N, we said, is going to be what?
3.
3, right? Let's go with L. What is our L going to be?
2.
2. And why is our L 2?
Because a 2 is a p atom or a configuration.
Okay, so can you remind us what our S is? So let's do this a side note just to have this S, P, D, and F. S would be what number?
0.
0. And P?
1.
Yeah. D?
2.
2. And then F?
3.
3, right. So in this case, our L would be what?
2. I mean 1. Sorry.
Right, our L would be 1 because of that. Let me change it there. Okay. Our ML. Okay, so bear with me with this one. So our ML is usually our range. So this L is telling us to go back, right, to our previous quantum number. And again, what is ML telling us?
The magnetic something.
No, that's good. Yeah. Your specific orbital. So now this one tells us our range for ML. So that means that we're going to go from -1 to 1. So we're going to say -1, 0, and 1. That's all what our ML is. So any questions on that one?
I have a question.
Yes, go ahead.
Where does the 0, 1, 2, 3 come from for the SPDF?
So this comes from our orbitals, and this goes back to electron configuration. It just has to do with our levels.
Oh, okay.
Yeah. So I would have this as a side note, just so you can remember. Does that answer your question?
Yeah.
Okay. All right, so moving on. So we have our last quantum number we said was
Spin.
our spin, right? What is our spin going to be? Is it going to be positive or negative? So it depends, right? And let's actually do this whole example. So we know that for this one, our range is going to be between -1 through +1. So we need to make sure we include 0. So let me do it in pink. So we have -1, 0, and 1. -1, 0, and 1. Now, how many electrons do we have again? Or how many electrons do we work with?
5.
5, right. So according to Hund's rule, remember we need to make sure that we fill it out, or we fill out 1 electron in each orbital first, and then if there's leftovers, we'll fill out the rest. And that's why Hund's rule is really important, because sometimes with these types of questions, you might land on a number that you're not supposed to, and you get the whole answer wrong. So like we said, there's 5 electrons, so let's do it. Let's fill this up. So 1, 2, 3, 4, and 5. And it landed on this one, right? And remember, we want to focus on the 5th electron. So this is our 5th electron right here. And is it facing up or down? I mean, it's pretty
Down.
down, right? So when it's facing down, we're gonna have a negative spin, negative 1/2. So with spins, I'm not sure why they chose a 1/2 or this number. I'm not sure why. But what I do know is if it's facing down, it's going to be negative 1/2. But if it's facing up, it's going to be a positive 1/2. Okay. Any questions on this?
Nope.
No? Okay.
I actually scoot back just a second, Jessica.
Mm-hmm.
You were going over the quantum numbers, and can you just go over the definition really quick of the ML and the MS?
Yeah, for sure. I
You
can
had a
go back.
nice definition you were right now, and I didn't get those last two. Yeah.
Okay. Yeah, these. And let me know whenever you guys are ready, okay? Yeah, so these are the 4 quantum numbers that you guys are gonna encounter or see.
I got it. Thank you so much.
You're welcome. All right, so let's do here, and let me write another little side note. You know that these are quantum numbers. Just so you guys can have this on your notes. So with MS, we said that if it's positive 1/2, you have an up arrow, and if it's negative 1/2, you have a down arrow. It's just a little side note. Okay. So what I'm gonna do, I'm gonna write down another example, but I want you guys to do it as a class. So I'm just gonna write what you guys are telling me, okay? So let's do 4D4. So break this apart for me. What do I do? Where do I start?
Figure out n, which is 4. Or, yeah, 4.
Okay. Sorry. So yes, you said start off with 4, and we said 4 was our what again?
N.
Our n. Let's write that side note n. All right. You guys are the teachers now. I'm just the student. We flipped scripts. So what else do I do?
So then ML, or is that right? No, what's the next quantum number? Or not number, but
Yeah, quantum number. You're right.
okay.
Yeah.
Would D be your L?
L, yeah,
Right. L.
be 2.
Yeah. L. Yeah. Good job, Cassie. Yep. Good job, everyone. So L is your 2. Yeah. What is our next one?
Magnetic quantum number, so ML.
Right. Magnetic quantum number. So M and that little subscript L. What would be that?
-2 to 2.
Right. -2 to 2. So -2, -1, 0, 1. And our last one?
Spin.
Our spin. Right. Do we know that one right now?
No.
Right. No, we don't know that one. We have to make sure we draw everything out. Okay. So our range is from -2 to 2. All right. So what do I do from here? Oh, so, you guys can annotate this. So how would this be filled out? Any brave soul?
I can try.
Okay. Yeah, feel free to talk amongst yourselves, you guys.
Okay. So it'd be like that because it's 4 electrons.
Okay.
And then from there, you would look at the direction of the direction the electron's pointing at,
Okay.
which is upwards. So I want to say +1.
+1.
Be
Yeah.
+1/2, right?
Or-
Right. Right. Cassie and Kayla, you guys are both correct. +1/2. And again, why is it +1/2?
Because it's an up arrow.
Right, it's an upward arrow. Right. So then we'll just write +1/2.
And you always pay attention to the last electron, right?
That is correct. Yeah.
Okay.
Our last electron, the 4th electron. Yeah.
Jessica, I have a question.
Yeah, go ahead, Cassie.
So can't you just count out your electrons based off of your ML? Does that make sense? So like you have 4, so can't you just start off at -2 and say 1, 2, 3, 4, see that it lands on 1 and knowing that it's an up and just assume? Or do you always have to draw it out?
That's actually a great question. And that's something that you have to be careful about. Because let's say you have
Okay.
4D9, or no, let's do 4D8. Ah, what can I know? 4D8, right? We know that we have 8 electrons. So if we were to fill this orbital out, we would do 1, 2, 3, 4, 5, 6, 7, 8.
Yeah.
Right? So let's say we fill it out, because sometimes what if you have a multiple choice, right? And they fill it out like this, or they fill it out like this: 1, 2, 5, 6, 7, 8. So in this case, our spin is the same, but there are cases where, let's say if it's 9, our spin will be different. So that's the reason why we don't want to assume that. And I understand what you're saying, like, oh, if there's 4, it's much easier, right? But what if you have more than 4 electrons? So this would happen sometimes where if you have a multiple choice, they're like, oh, which one is the correct one? And if we assume that we can just count them out like that, we would get the answer wrong. So we have to make sure that we fill it out the way that we're supposed to, if that makes sense.
Okay.
Yeah, but that's a good question. Yeah. Yeah, when I took chemistry, I was doing that and I would get some answers wrong. Um and then Dr. Henry was like, "Oh, well, what if this happens?" And I'm like, "Oh, yeah, you're right." So just
Okay.
be careful of that. Yeah. Did
Okay.
that make sense?
Yeah, I did.
Okay. Right. I feel like you guys got this. Okay, let's do another example. I'm just gonna write down the example and you guys help each other, okay? So the next one would be 5F13. So anyone can start this off.
Okay, so 5 is your N, right?
Mm-hmm.
And then your F is going to be your L value. And then you've got 13 electrons.
All right. So now pretend you guys are tutoring me now. How would you explain this to someone who doesn't know?
So like he said, n equals 5. And then your L would be 3 because it's an F. And your magnetic quantum number, it would be -3 to 3. And then you'd have to write that out, the configuration.
All right. So would anyone like to volunteer to write it down? How would it look like?
Would it look like this? Oops. Sorry, that was my alarm.
Okay.
I lost count, but I want to say because it's 13 electrons. And then with the number, oh no, wait. Oh, wait. So it'd be like, I want to say it's like that.
All right. Does everyone else agree?
Yeah.
I agree.
Okay. So then therefore what is our spin for this one, for this quantum number?
Be negative, right? -1/2.
Right, -1/2.
Because it's a downward arrow.
Correct. Because it's
Where? Where's the downward arrow that you're looking at? Okay, so whatever it stops at. So why are we looking at that particular downward arrow? I think Cassie circled it.
Because that's your 13th electron, because you're paying attention to this right here.
So how is that the 13th electron and not the 12th?
Because that's the last one you put in.
6, 7, 8, 9, 10, 11, 12. Oh yeah, that is only 12.
Hund's rule, you guys.
So
How
you'd
did-
have one right here.
Well,
But
remember, we
it's
talked
still
about-
facing down, Matt. So nothing changes.
Okay, so with this extra orange arrow Isn't there 14? That extra orange arrow?
1,
There's
2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. No. So then this goes away. It's still, yeah, it's still down.
Wait,
And-
so if the arrow was up, would it change?
It'd be a positive 1/2.
Okay.
I'm so sorry, you guys, but why are we counting this downward arrow and not the standalone upward arrow because of Hund's rule?
That's correct.
So you're counting the last one that has a pair.
It doesn't necessarily have to have a pair, because let's say you have something like this, right? And let's say that it's 3d3, right? Something like that. We know that we have 3 electrons, and our last one that we drew just happened to be this one, and it's facing upward. So our spin would be positive because of that. So let's say you have 3d4. So according to Hund's rule, remember we need to make sure we fill out each orbital first, and then we add the last one. And this last one just happened to be with a pair, and it happened to be downward. So this one would be negative 1/2. Does that make a little bit more sense, Matt?
Kind of, but I'm still not understanding why we circled this 12th electron up here and not the 13th.
This is not.
That is the
That is the 13th. It's not the 12th, it's the 13th.
Remember, because we put in the downward last, so that's the last one we drew.
Here, Matt. So I'm gonna have you actually draw this one out. I'll draw the lines, and you draw the electrons that are supposed to be drawn on there. So we have -3, -2, -1, 0, 2, 3. Okay, so fill this out according to Hund's rule to see what happens.
Or the same problem we're working on?
Right, the same problem. So you can see why that one is the 13th electron. So fill it out how you're supposed to.
1, 2,
Oh.
3, 4, 5, 6.
Anyone want to explain to Matt?
Up arrows first.
Yeah.
This is an upward arrow.
Yeah.
But you're
up
putting the
for
downward
each.
with it. You have to fill in the ups and then you put in you go back and fill in the downs.
Okay.
So that's how you're counting wrong.
I understand.
Yeah.
And why do we do this, you guys?
Because Hund's rule.
Hund's rule, and what else? Electrons are introverts, right? They don't like sharing a space unless they have to.
This is becoming a little bit confusing for me, but I'm getting.
7, then 8, 9, 10, 11, 12, 13. I understand. Okay. So that's where you get the 13 because you got to do the up arrows first.
That's why you could just pay attention to what number, like how many you have.
Mhm.
And then that's when you pay attention to where it stops at and look at what direction the arrow is facing.
Okay.
Yep.
And
So-
then,
Oh,
no, go ahead. No, no.
no, mine was non-related, kind of, but go ahead.
One more time. Why do we start out with the -3, -2, -1, 0?
Right. So
The magnetic
would
quantum.
you like to explain that?
So you see your L,
Yeah.
that relates to your ML. So if it's if it switched to 2, it would be -2 to 2. And then
Okay.
if it was 3, it'd be -3 to 3. So you see where I'm getting.
Okay.
It's just your range.
Yeah.
based on your L.
Okay.
So Matt, if it was, let's say it was a 4, our L was a 4,
Hmm.
what would be our ML?
So would that be -4, -3, -2, -1, 0, 1, 2, 3, 4?
Yep.
Okay.
Mm-hmm. No. And then I think I heard Abby, where you said you were a little confused?
Yeah, I was a little confused, but right now that Cassie explained it, I kind of got it why we had to stop at there for 13.
Okay, so do you want to explain to me why we have to stop there, just to make sure? So why that electron?
So from what I understand, since we're looking at the top, it says 13 electrons. We have to count first, like putting the ones that are going up, and then the ones coming down, and then right where the one that comes down, that's where we know our place, and that's why it would be 13 and not like we were thinking of why the only pair being there.
Right. Yeah. Let me write more notes so you guys can have.
Just I have a quick question.
Yeah.
So for MS, it's either positive or negative 1/2.
Right. It's either positive or negative 1/2. And remember, our last electron that we fill out in that orbital tells if it's positive or negative. So remember, if it's facing up, it's positive 1/2. If it's facing down, it's negative 1/2.
Okay.
Mm-hmm.
Yeah.
The 1/2, I don't know why it's 1/2. But the only thing that you guys should know is facing up, it's positive. Facing down, it's going to be negative. So that's why you want to make sure that you follow Hund's rule and then you fill this out accordingly, because if you don't, your spin is going to be off.
Okay. Yeah.
So I think I read this, but so if you have a non-paired electron, say if there's like a couple left out, the more magnetized it is.
Yeah.
Okay.
Then there's these definitions. There are paramagnetic and there's diamagnetic. So paramagnetic, and let me just change the page. Paramagnetic, yeah, is elements with unpaired electrons. And then that E with a little dash is just electrons. And diamagnetic are completely paired electrons. Oh my gosh, I'm so bad at spelling. Completely paired electrons. So if we take a look back at the example that we did, our previous example, would you say that this electron configuration is paramagnetic or is it diamagnetic, and why is it the way it is?
It para because there's unpaired at the end.
Right, that is correct. So even though we see that these are all paired together, they're not all paired. You still have that one lonesome electron, right? So it would be paramagnetic because there's one pair of electrons that is not paired. Okay. Did that definition make sense to everyone?
Yeah.
Okay.
It's paramagnetic because there's one standalone electron at the end.
That is correct. Yeah. We go back to your definition. Yep. So paramagnetic are elements with unpaired electrons. Diamagnetic, remember di meaning two. Diamagnetic, they're completely paired electrons. Okay, so this one, I want Abby and Matt to work on this one, okay? I'm gonna write it down and you guys give me all the quantum numbers and how we've been doing. So if we have, let's do 4D.
Real quick before we keep moving on, it was dimagnetic, paramagnetic, and diamagnetic. Okay. All right.
Yeah. Let me know when you're ready and then so we can move on.
Okay, we're ready. Well, yeah.
All right, Matt, let me know when you're ready, okay?
I'm ready, I promise.
Okay, all right. All right, so Matt and Abby, you guys are the teachers. What do we do? What are our quantum numbers? Where do we start?
Okay, so we're going to start out with our n equaling 4, and then our d is our L value, so that's going to be 2, and then we have 9 electrons. So my ML would be -2, -1, 0, 1, 2. So then I need to write out my orbitals.
Okay,
Like that.
right.
And then I've got to do my 9 electrons, right?
Yeah.
So whoop. That'd be 1, 2, 3, 4, 5, 6, 7, 8, 9.
And
So
I'm gonna stop you real quick, Matt.
okay.
So when you draw the electrons, they're negative, and you know how like magnets, if you put magnets with the same charge, what do?
They repel.
They repel, right? So
Yeah.
we're gonna see it, or we're gonna write or draw these that way. So these are the charges, right? This top part of the arrow would be like our negative charge. So we want to make sure that the other charge is repelling. So we're going to draw it like that.
Oh, okay.
Okay.
I got you.
All right. Ah, so sorry. It's all yours now.
Like this.
Yep.
Okay. Thank you. And then this is going to be the 9th right there. And it's pointing down. So that's going to be a -1/2 for your MS.
Yeah, magnetic spin. Yep.
And this is paramagnetic
And why is it paramagnetic?
because you have an unpaired electron at the end.
Right. That's correct. You have an unpaired electron at the end. Yep. Yeah, you did a great job, Matt. Did that
Thank
make
you.
a little bit more sense?
I felt like this one was easier than the one before. Maybe because I finally understood it.
All right. So Abby, I'm gonna give you another example, okay?
Okay.
And I want you to do that one.
if I can do well.
All right. And Matt, so do you have any questions on that one? I feel like you were pretty straight on.
Yeah, that was fun.
Okay. Let's go on. Oh, another one. Okay. So here you go. And Abby, pretend that we are the students and you are the teacher. Okay.
Oh
So
my God. Okay.
pretend to us as if I've never taken chemistry in my entire life. 5F7. And if you want, you can phone a friend.
I'm definitely okay. Let me see. How do I do this? Is it annotated? Okay, so this will be. Where's my pencil? Oh. This one will be our N. And then, if I'm correct. Well, I can't even draw it. And this will be our electrons.
Okay.
Sorry, guys. I write horribly. So we know that our N will be 5. Ooh. No. Oh, wait. Okay, I'm stuck here.
All right. So Matt, can you help her out? So
Help me out, man.
So, okay, so you've got your N, which is 5, and then the next thing that I would do is look at your L value, which is your F,
Yeah.
and then this is when you need to look at your like your value block, and F holds a 3 orbital,
Okay.
so L would equal 3.
Thank you, Matt.
Welcome.
And then our M. Sorry, guys. Ugh. Equal. So then we have -3. Oh my God, I can't write. A 2 and a 3. And then we have to go with our electrons. Okay, so then we're gonna do 1, 2, 3, 4, and 5. 6. Wait a second. Sorry, I messed up. Hold on. What? Five, 6, and 7. And this would be our 7th electron. And because it's looking down, it would have to be. Wait, I'm missing this one. Sorry. Okay, so far I believe I'm right. Wait, hold on. So this would have to be our 7th electron. So go 1, 2, 3, 4, and then we go 5, 6, 7. So then we have a lonely pair.
So I'm gonna stop you there, Abby.
Yeah.
So if we take a look at our ML right here, right?
Mhm.
This tells us our range. So -3, -2, -1, 0, 1, 2, 3. And all those numbers are gonna be orbitals. You see that?
Yeah.
So what is the difference between yours and the bottom one?
Oh my God, I'm so sorry. There,
Don't apologize for learning. So
I have too many orbitals. From here, I'm missing one more.
you have 1.
2.
You're missing the other half, right?
Yeah.
Yeah, I'll draw them out for you. 1, 2, 3. All right. So now how would you fill out the orbitals?
So, here you go. 1. Oh, no. 7.
Right. Okay.
So now, sorry. So now that since my 7th goes all the way here and they all have like no pairs,
Mhm.
that would create a big change, wouldn't it?
Yes. Yes, it would. So what is our spin now?
So our spin would have to be, since it's going up, would have to be positive.
Right. Yeah. So remember, keep in mind that your ML kind of gives you the range as to how you're supposed to extend those electrons.
Okay.
Okay. Yeah,
So
positive.
then it would be a positive 1.5. Is it positive 1.5? No.
Yeah, that is correct. It's always half.
Oh.
It's either positive or negative.
Okay.
Yeah.
Okay. So because these were remaining like going up, it would be a positive.
Right, because this was your last electron, right?
Yeah.
Let's say this was 8. So your last electron would have been here, right?
Yes.
So now our spin would be what?
Our spin would have to be negative.
Negative, right? Yeah. Does that make sense a little bit more?
Yes, I'm sorry. I'm getting there. I'm trying.
No, it's fine. It's fine. Okay. So also, if you take a look, let me draw. So that's why it's also important to fill it out according to Hund's rule, because 1, 2, 3, 4, 8. There's 8 electrons here, right?
Yeah.
And there's 8 electrons here, but your spin here is negative, and here it's positive. So do you see the importance of Hund's rule? You have to make sure each get a room first, and then if they have to share, you can add the other electrons.
Okay.
Okay. If you have any questions.
No, I think you explained everything perfectly. So I just have to remember that, my ME is going to be how many spaces that I have to draw.
Yeah.
Yeah. ML, sorry.
Okay. Okay. All right. Anyone else have any more questions? This is it for today. This was the topic for today. But do you guys have any more questions, or do I need to clarify something else?
Oh, thank you for going over it so slowly. I appreciate that.
Yeah, of course, of course. I'm your SI. I'm here to help you guys out.
Jessica,
you.
Yeah, thank you.
there's pictures on the homework that's asking relating to the quantum numbers. How do we do those?
Do you want to share the screen so I can see them? Can you share your?
Yeah.
Let me stop sharing mine. I'll look at that, Cassie, and then I'll email all of you guys in one big email.
Yeah, because there's, like I said, there's a few more.
With the same, like similar questions.
Yeah, like what's the angular node?
Yeah, Jessica, if we could just maybe verify with Dr. Henry, if we're gonna have more than 3 more days to do the homework, or
Right, yeah, I'll reach out to him. Do you guys want like another week, or how much time do you guys want so I can negotiate with him?
I mean,
Because there's I saw right now as Cassie was sharing her screen, there's a lot of things you guys haven't really talked about yet.
right.
So definitely I can ask him. I'll ask him if he can extend for another week. Or do you guys, is that
Or
fine?
maybe I was gonna say at least until like Monday.
Okay.
Yeah, I'd say until Monday. Well, at least for me, but
Yeah, because
Try to work on it over the weekend, and then if we have questions, we can
okay,
talk
yeah.
about them.
I'll let him know then. Yeah, so you guys have, so you can have more time to work on this stuff. Any more questions?
Excuse me, I'm doing pretty good.
Okay. Yeah, I know February is let's see, it's an interesting month. And this happened to me too when I was taking this class during spring semester, where there's things going on like Black History Month and all that stuff. And sometimes Dr. Henry like wouldn't have time um, to teach certain things because of that. So that happens, or I noticed that happened every year. Or speaking of Black History Month, did you guys submit anything?
I emailed him. I wasn't able to submit it, so I just emailed him.
Okay.
So hopefully he got it.
All right. Yeah, make sure you guys attend to so you guys can get extra credit. Well, I guess I'll let you guys go. And again, I will take a look at my notes and I'll email all of you guys in a whole email. And again, if you guys want to come to tutoring as well, like we can help each other out. And if you have any questions, feel free to email me as well.
When was tutoring again, Jess?
Um, they're on Tuesdays and Thursdays from 6
Okay.
to 9. Yeah.
Okay.
Yeah, the link is posted there. So if you just click on the time, it'll direct you to the Zoom meeting.
Okay.
Yeah.
all right. Thank you. Appreciate
Welcome.
it.
Yeah, of course. Well, enjoy the rest of your day, you guys. I texted Dr. Henry asking if he can extend it. So hopefully he says yes. And I'll let you guys go so you guys can do your stuff.